In this lesson, we will review a few of the probability concepts that we've learned over the last few lessons. We'll talk about conditional probability, independent events, and dependent events. Look, here are a few of the formulas that we've learned dealing with probability. One thing to keep in your mind is if we're dealing with A or B, you're usually going to wind up adding. Whereas if you're trying to find the probability of A and B, then you're going to be multiplying. And then you have conditional probability, all right? The probability of A given B is equal to the intersection of A and B divided by the probability of the given part. Notice that it has to be the given. All right, given B, we're dividing by B. Back on this first formula, notice that basically we're subtracting the overlapping part. So if you want to find the union of two probabilities, all right, the probability of A or B happening, you can add the individual probabilities, but then you need to subtract the overlapping part. Anyway, we'll see how these formulas get used as we look at specific problems. By the way, so these are the versions of the formulas where I'm using the words or and the word and. Okay, but everywhere you see the word or, I could use a union symbol, all right, because it means the same thing. And everywhere you see and, I could use an intersection symbol. So here are the same three formulas written with the union symbol for or, A or B, and an intersection symbol, but it still means A and B, and this still means A or B. So please be familiar and comfortable both ways. Alright, anyway, those will come up again. So let's take a look at the first problem. The medal distribution from the 2000 Summer Olympic Games is shown in the table below. Choose one medal winner at random. Okay, now problem number one. Find the probability that the winner won the gold medal given that the winner was from the United States. Alright, so they clearly gave us this word given. And when they do that, it makes it sort of easy. If they're giving us that the winner was from the United States, then what you do is you circle that part of the chart. Alright, we're going to circle the United States part of the chart. Okay? For the rest of this problem, we can ignore everything else. Just cross it on out because our universe just got a lot smaller. Only the United States is going to matter for the rest of the problem. Now we look back to see what was the probability they were really asking us about. Okay, the problem said find the probability that the winner won the gold medal. So, alright, so gold medal is right here. So probability is target over total. So our target is gold medal, so that's 39. And our total is going to be the sum of these three. So 39 plus 25 plus 33. I'm just going to put that in my calculator. 39 plus 25 plus 33. That is equal to 97. So that's the total. So 39 divided by 97. Alright, that probably does not reduce, but let's just check it out. Alright, 39 over 97. Alright, it does not reduce. So you could just write the you could write the probability just like that. Of course, you could also put it as a decimal. If you use a decimal by toggling it, you need to write 4 decimal places. 0.4021. Got to round up. And of course, we could then write that as a percent very easily. 40.21% probability. Okay, problem number 2. Find the probability that the winner was from the United States given that he or she won a gold medal. So let's erase the well, that's not the eraser. Whoops. Okay, find the probability that the winner was from the United States given that he or she won a gold medal. So look at what we're given. All right, because of this, given that we're talking about a gold medal, then that means let's circle that part of the chart. So we're given that he or she won the gold medal. All right, so we can forget about the rest of the data. Let's cross it out so we won't be tempted to use it. Now, what are we trying to find again? The probability that the winner was from the United States. All right, target over total. Our target is United States. Okay, we're being a little egocentric today. It's all about us in both problems, but that's okay. So 39 is a target. Now, out of the total, so the total is going to be the total of all of these numbers. So I think I'll just do that off camera, but I'm going to add up all of these numbers right here. Alright, so the total is 301. So 39 over 301. Now I'm betting this won't reduce either. 39 over 301. Okay, that didn't reduce. As a decimal, it would be 0.1296, got to round up. Which would be approximately 12.96%. Okay, so that's how you do this is called conditional probability when we deal with the given that and we narrow down the universe. Okay, so it looks like we're moving on to a different type of problem. Alright, so this is going to be a nice little review for us. A medical research laboratory where a drug that promotes hair growth, I could kind of use that, in balding men is being tested. The results of the preliminary tests are shown in the table below. Choose one test subject at random. Alright, now find the probability that a test subject's hair grew given that he used the experimental drug. Alright, are we still doing the given that problems? I thought we just mastered that. I was kind of hoping we'd have a different type of problem now. But okay, guess we're doing this. Given that he used the experimental drug, so that means we will circle that part of the chart. Alright, which means we're only looking at this part. Alright, using of the drug part. Placebo, that means a fake pill, like a sugar pill that has no effect. So anyway, we're going to cross that out because that's not what the part that we're given. Now we look back and say, what are we trying to find? The probability that a test subject's hair grew. Okay, so target over total. Hair growth is our target, and our total is, if we add these together, so that's going to be 2,400 if we add those up. So probability target over total, that's going to be 1,600 over 2,400. Okay, we can begin to simplify this mentally. All right, dividing both of these by 100 would be 16 over 24. Both of these are divisible by 8, so that would be 2 over 3. So 2/3. So that's the probability right there. As a decimal, this would be 0.6667. And as a percent, this would be 66.67%. Okay, so there you go for number 3. Alright, look at number 4. Find the probability that a test subject used the placebo given that his hair grew. Alright, look at what we're given. Alright, so we're given that hair grew. So let's just focus in on that part of the chart. Okay? Given that his hair grew, hair growth is this part of the chart. We will therefore cross out this part of the chart. okay, because that's not part of our universe anymore. So now, what are they asking us for again? The probability that the test subject used the placebo, the fake drug that doesn't do anything. Alright, so that's our target, is placebo. So here's the placebo number right there. And again, so we'll need the total for this row. So let's see, 2,800. Yeah. Alright, that's the total. So target over total, placebo over total. So 1,200 over 2,800. Okay, dividing by 100, see the two zeros in the numerator and denominator? So we can see mentally that this will be 12 out of 28. Both of these are divisible by 4. So if I divide these by 4, 4 goes into 12 3 times. 4 goes into 28 7 times. So that's 3/7. And I could make that into a decimal if I felt like it. 3/7. That's 0.4286. Got to round up. Alright, so that's 42.86. Running out of space there. Okay, but it's there, trust me. 42.86%. Okay, that's how we do that. Alright, hopefully we're all done with that type of problem, because that's plenty, and we're really super good at that type. Alright, moving on to some of this. Let's see. Use the definition of independent events to determine whether the events from rolling a number cube die are independent or dependent. Okay, so the odd event, the event odd and the event 3 or 6. Alright, and so in our formula we have events A and B. Alright, and so we have two events here. The first event is that we get an odd, and the second event is that we either get a 3 or a 6. Okay, so let's call this event A, and let's call this event B. So we're supposed to prove mathematically whether or not these two events are independent by checking to see if the intersection equals the product of the individual probabilities. Now that's a lot of words, but basically we're checking to see if this formula works. If it does, independent. If the formula is not true, then we'll say dependent. Okay, so maybe underneath where it says independent or dependent, we'll write works, alright, talking about the formula. Either the formula works for independent or it doesn't work for dependent. Either it works or not. Independent, dependent. Anyway, so let's figure out the probability of A and B happening. Okay, let's think about this for a second. Alright, so remember, event A is rolling odd, and event B is rolling a 3 or 6. So our first job is to find the probability of A and B, okay, happening at the same time. In other words, the overlap between these two categories. Alright, you can probably just do this mentally. What's the overlap between the odd numbers and the numbers 3 or 6? Yeah, it's just the number 3 is the only thing that's that these two sets have in common. Alright, odd numbers and the numbers 3 or 6. Well, 3 is the only one. This set only has 2 numbers in it, and 3 is the odd one. So, so 3 is the only thing that they have in common. So basically, what's the probability of rolling a 3? Well, there's only the 1 3, so we have 1 chance in 6. So 1 out of 6 is the probability of A and B happening at the same time, because it would have to be a 3 for that to be true. All right, and there's only one of those. So what we just found was the probability of A and B. Okay, so that's the first part of the formula. I replaced the intersection sign. It means and, so I'm just showing that it's the same thing. So we found this. It turned out to be 1/6. Now, let's find the probability of A separately. Okay, back to the black screen. Okay, so now we're just finding the probability of A. Forget about B. Okay, now the probability of A, well, A is odd. So what's the probability of being odd? Yeah, it's 1/2. Okay, well, technically, there are 3 odd numbers on a number cube, right? 1, 3, and 5, out of a total of 6 numbers. So 3 in 6, which, quickly it reduces down to 1/2. So that's the probability of just A. So let's write that down. Okay, so probability of A is 1/2. All right, now let's find the probability of just B. All right, event B is rolling a 3 or 6. So what's the probability of event B? Well, event B has 2 chances. All right, there's 2 ways, 2 targets out of a total of 6 numbers on the cube. So that quickly reduces down to 1/3 if I divide both of these by 2. So the probability of B by itself is 1/3. Okay, so let's write that down. 1/3. Okay, so we filled in each of the parts of this formula. The probability of A and B, the probability of A, and the probability of B. Now we're supposed to check this formula and see if the formula actually works. If so, then we'll declare these events independent. So does 1/2 times 1/3 equal 1/6? Well, sure, because you just multiply straight across. 1 times 1 is 1, 2 times 3 is 6. So the equation does hold. So that means, because it works, that means it must be independent. These events are independent. All right, if it doesn't work, then it's dependent. Let's do the same thing for problem number 6. Okay, so we have, once again, we have 2 events. The first event is less and 3. I think they meant less than 3. I think that's a typo. Less than 3. And event B will be more than 5. So let's call this event A, and we'll call this event B. All right, so once again, we need to find the intersection, the overlap between these 2 sets, and then we need to find the individual probabilities and see if they multiply and equal each other. So maybe I won't need to cut over to the black screen this time. Let's see if we can do it right here. So less than 3, more than 5. What are the overlapping numbers between those 2 sets? Well, there are 0 numbers in that overlap. There's no overlap between these 2 sets. All right, there are no numbers that are less than 3, and at the same time more than 5. That's not happening. So that probability is 0. So that the overlapping probability is 0. Now, so this is not looking good to being independent. Now, the probability of A, probability of being less than 3, Well, remember, a number cube, it goes 1, 2, 3, 4, 5, 6. So as far as being less than 3, there are two of those numbers, 1 and 2. So the probability there is going to be 2 out of 6. And of course, 2 out of 6 reduces to 1/3. Okay, so that first probability is 1/3. I mean, I could have left it 2 out of 6, but I just feel like reducing. Now, let's look at probability B by itself. More than 5. Okay, looking at these possibilities again, more than 5, there's only one number bigger than 5, and that's 6. So the chances of rolling that are 1 out of 6. Of course, these are not going to multiply together and give us 0. Okay, 1/3 times 1/6, in fact, would be 1/18. So it's certainly not 0. So that means this equation is not true. So these events are not independent, they are dependent. Okay, because it didn't work. All right, when it doesn't work, it's dependent. Okay, let's do the same thing for number 7. See if I can get that formula cut and pasted, my friends. Okay, once again, we're going to check out this formula. So, what do we have? The event A will be even, and event B will be prime number. Okay, I'm going to go to the black screen. Okay, so event A was even, and event B was prime number. Okay, and we are supposed to find the probability. Right now we're going to find the probability of A and B. But first of all, remember we're talking about a 6-sided number cube. So overall, a 6-sided number cube goes like this. It goes 1, 2, 3, 4, 5, or 6. Those are the possibilities. Okay, so of course the even numbers are 2, 4, and 6. Now, maybe I should have made those yellow. Alright, the even numbers are 2, 4, and 6. Now the prime numbers are the numbers that can only be factored as 1 and itself. Now 2 is a prime number. Alright, it's the only even prime number because 2 can only be written as 1 times 2. It can only be factored as 1 times 2. Now, what else? Okay, 1 does not count as a prime number. 2 is a prime number. 3 is a prime number. Okay, 4 is not a prime number because that's 2 times 2. 5 is a prime number. And 6 is not a prime number because 2 times 3. So the yellow numbers here, these are the even ones. The green numbers here, these are the primes. Okay, so looking back at the formula, the first thing we need to find is the probability of A and B. In other words, the overlap between the two sets. Okay, so what's the overlap between these two sets? What do they have in common? This is the only thing they have in common. They both have 2, the number 2 in common. Okay, so they only have one thing in common. So that means that probability is going to be 1 out of 6. Only one number out of the 6 total. That's what the overlap is. 1 chance in 6. So let's write that down. So the probability of A and B is 1/6. Okay, now let's check the individual probabilities. What's the probability of A? Okay, so now for the probability of A, we're just looking at these yellows. There's 3 of them. Alright, so the probability for A, and I guess I should just write this down, the probability of A is 3 chances out of 6, which is 1/2. Okay, great. So 1/2. Now how about probability B? Well, probability B has the same thing going on. Probability of B, it also has 3 chances out of a total of 6. So that is also 1/2. Okay, so the question is, are these events independent or dependent? Yeah, these events are dependent. Alright, because 1/2 times 1/2 is 1/4, not 1/6. Okay, so those events are dependent. Change that equal sign to a not equal sign to emphasize that the formula did not work. Dependent. Alright, looks like we have one more of these. Okay, event A is more than 4. And event B is 2. Okay, so let's find the intersection. Because once again, we are checking this formula to prove whether or not they are dependent or independent. So let's start by going to the black screen. Alright, event A is more than 4. Okay, these are the numbers that are more than 4. So the probability, actually, let me not say the probability of A yet. Maybe I will. Anyway, the numbers more than 4, like we said, are 5 and 6. Okay, for event B, I'm sorry, what was event B again? I got distracted. Event B, my friends, was simply the number 2. Okay, so obviously, Shazal. Alright, this is a strange little situation because what we're supposed to be finding now is the overlap between these two. We're supposed to be finding the probability of A and B, the overlap. 5, 6, 2, yeah, they have nothing in common. Okay, so that probability of picking a number that's both at the same time, that's probability of 0. So if we blindly fill that into the formula, then on the left side we're going to have to put a 0. The probability of A by itself, let me just go back and do my colors. The probability of A by itself, well, I have 2 chances, alright? 2 chances out of 6, which equals 1/3. Alright, the probability of event B by itself, well, I have 1 chance for event B. So it's 1 chance in 6. So I have 1/3 and 1/6. So showing my work properly, 1/3 times 1/6. Alright, clearly 0 does not equal 1/3 times 1/6. In fact, this would be 1/18. So what are we going to put right here? Dependent. Alright, that is it. my friends. Yeah, that's all. That's it for this lesson. I hope it was helpful, and I will see you on the next video.